All right, I'm Vlad, and I'm going to be talking about binary dependencies.
Just do it.
Just doing it.
Just do it.
All right, so we want to be able to identify the dependency graphs of all packages generally, ideally, but specifically keystone packages. What are keystone packages? Nadia, in her book, in her report, has this great definition where it comes from sort of this biology definition, and the keystone package we want to say is a package that has a widespread effect on its ecosystem, right? So something that is disproportionately useful or dependent upon by other things or whatever. So especially the most important packages, we will really want to know their dependency graphs. There's two reasons for this that I'm going to talk about. The first reason is open source financial sustainability. So obviously, open source maintainers don't get paid enough or at all. Burnout is a big issue. When you have burnout, packages don't get maintained. You know the deal. And open source supply chain security. So if we don't know any particular package's dependency graph, we can't know what security issues it might be vulnerable to. So the first thing, open source is not financially sustainable. Companies charge money for their products. Their products incorporate open source software. The money goes to the companies. It doesn't flow to the open source product, the open source packages. And so maintainers can't sustainably maintain their packages. This is a problem. Technically, this is according to the rules. Yes, open source licenses allow this, but also this can still be bad even if the rules say that it's fine. Both things can be true. I'm not going to go into a lot of detail about that. Miranda Heath is doing a great talk tomorrow in the community track about burnout in open source. So there's really powerful points about that. And then you can also reach out Whitaker's blog post, The Open Source Sustainability Crisis. So here's an example from my work. I work on the Open Source Pledge. This is an initiative where we try to get companies to pay the maintainers whose work they depend on. We ask companies to pay $2,000 per full-time equivalent developer that they employ per year to any open source maintainers, really, but particularly to the maintainers of the software they depend on. The money goes directly to maintainers. We don't handle any funds. We had our 1-year anniversary last year, and so far our members have raised $6.1 million for maintainers, which I'm very happy about. But, thank you. But where should the money go, right? So obviously companies don't understand 100% of their dependency tree, and so don't know necessarily what the best way is to allocate all of that money that they're paying. And like I said, we struggle to identify especially the most important packages that keep our global infrastructure running. So that's one problem. Another problem is open source supply chain security. So let's say you have a thing and it depends on fulib and it depends on some other lib and some other thing. And there's a security problem in that last one. You might want to know because that means that there might be a security problem in your project. But if you don't know about that package, you can't do anything about it. So that's bad, and we want to solve that. So we want to be able to identify packages dependency graphs. Now, you'd think, look in the manifest, right? Because it says in package.json what things depend on. The problem is some things are not in the manifest, the dreaded phantom dependencies, which are sort of described in this really cool post. So if the dependency is not in your manifest, you're not going to know you depend on it, and then you can't fund the people you depend on if you wanted to do that. And also you can't spot security issues from the stuff that you depend on. So that's a problem. Now, I'm going to talk about, there's different kinds of phantom dependencies. I'm going to talk about one kind, which is binary dependency. So this is when you have something, and then it calls into this dynamic library, which is usually written in C. And, this kind of dependency is usually not recorded. So for example, you might have some Python code, and your Python code depends on NumPy, but NumPy depends on OpenBlast. But it doesn't say that anywhere, so we don't know that. So that's bad. It's not in pyproject.toml, so you can't support the developers of OpenBlast or any of the other sort of binary dependencies that you rely on. And you can't track security issues in those packages, so that's not good. Now, how binary dependencies work, I wrote a post. It's on vlad.website. You can read it. I'm not going to get into it, but I will get into this specific thing. So how you usually call into C code in a lot of different ecosystems. So this is true for Python and Ruby and JavaScript. The details are a bit different. But basically, you want to be able to have some kind of code that you write that calls into the C library, but you also want to be able to manage type conversions in between the C types and your Python data structures in a way that is maximally flexible. And so what a lot of ecosystems do is you have this thing called an extension module, which is a bunch of C code. You write it's a little bit. You write a little bit of C code, and then that C code includes some headers. It's like python.h or whatever, and those headers tell it about the types in Python. And so that means that in your extension module, you can convert things, back and forth whenever is best for you. It's a performance decision. But anyway, the point is, your Python code and your extension module are going to communicate in whatever way is defined by your ecosystem. But then your extension module itself gets compiled to a dynamic library. This is the important sort of point, right? And your dynamic library is going to get linked dynamically to the C thing you're calling. And so that means that your compiled extension module, if we can get a hold of that, is going to say in it what libraries it needs, right? That's cool because then we can figure out what binary dependencies you depend on. So Python wheels, right, include vendored binaries. So, if you depend on OpenBlast, it's going to include a dynamic library, a compiled version of OpenBlast in your wheel. So that's good, and we can detect that. So let's investigate. I looked at the 15,000 most downloaded Python packages. I could only download 13,874 of them for various reasons. And of those wheels, 1,531 wheels contain dynamic libraries. So that's already interesting. And I found a total of 12,137 SO files. Now, those SO files, some of them are bundled binary dependencies, so stuff like OpenBlast, but some of them are just those extension modules that we wrote, that we just looked at. So, it's either the extension modules or the phantom dependencies, so we want to find the phantom dependencies. Okay, how do we find it? In your extension module, that's on Linux at least, it's an ELF file. Your ELF file has a section, the dynamic section, and in there it has a bunch of information, but some of that information has a tag, and the tag is DT needed. So it describes a library that your extension module needs. And in the name, it's going to tell you the name of that dynamic library. And it's that name that the runtime linker uses to find that thing on the computer. And so in theory, the name is sufficient for us to find it, right? So we can look inside the dynamic, those dynamic libraries and find those names. And so I decided to figure out what the most common dynamic libraries are in our 13,000 odd wheels. Some of them are obvious, I think, libm, whatever. So that's fine. But some of them, maybe you all know all of these things, in which case that's super cool. I don't. I know like a few of them, but I also wasn't expecting them to be this common. Other ones, I just don't know what they are at all. So anyway, I don't sort of have a concrete breakdown, but it's interesting because there's a bunch of stuff that's really dependent upon that we don't know. I don't know what it is. And so I wanted to come up with a number of how common binary dependencies are in the Python ecosystem generally. It's going to be a very inaccurate number, but let's give it a try. So we have 13,000 odd packages. We have 1,531 wheels that contain the SO files. We have 1,303 other wheels that depend on those first wheels, right? So that gives us 2,834 wheels. Now, when we generalize this, we're going to keep in mind that this is obviously a small sample, even though it is the most popular packages. And also, this is only one way of doing binary dependencies, right? There's other ways. But taking that into account, if we were to average that out, we can say that around 20% of Python packages have phantom binary dependencies, which means that for those packages, which is a lot of packages, we don't have the full picture of the dependencies, especially since frequently, you're not going to have a binary dependency for something that's like a left pad type situation, I hope. So it's going to be a thing that you really rely on, right? So we want to know about those things, and this affects pretty much everyone. It affects users of the open source software, and it also harms maintainers because the maintainers can't get supported. So I'd like to continue working on this. This was just for Python. We can do this in more detail for Python. We can do it for all of these other ecosystems. We could look at the symbols inside the dynamic libraries in case we have some trouble identifying what library a file belongs to. We can look at the symbols and build a database of, which symbols are provided by what package. I would like to publish some kind of tool that makes it easy to explore these binary dependencies for any given package, and integrating into services like ecosystems would be great. I'd love to get some funding to work on this. If you know of anyone that might be willing to fund this, let me know. And that's it. Thank you very much. There's more details on my website. All right, let's do some questions.
I'll fund you.
Amazing. Easy. Thank you very much. It's not a question, but I welcome it.
It's kind of a question. Can I fund you?
Sorry, the answer is yes to your question. Let's do a different question. We have a question over there.
Do you think package repositories should just forbid these kind of binary dependencies?
I don't. Yes. So, do I think that package manager or package managers? Package managers. Yeah, like registries should not allow these kinds of binary dependencies. No, I don't think so. I think if anything, we need to get better at handling them because there's a lot of people use them for very good reason. If anything, we don't have the infrastructure right now to do that in a reliable way. But yeah.
Just one word. There's a Python announcement proposal called PEP 725.
Yeah.
To add support for tracking pearls. And we have the author right there. Raise your hand.
Hello.
To track binaries that are rendered in Perl. There's another thing. Nama-san, please raise your hand. So maintains a package called STRA, SSTRA, which instruments GCC and LLVM builds to inject all the dependencies in an ELF section.
So to repeat what Philippe said, you said there's two. So there's PEP.
You have an ELF and then you know the dependencies because they were bundled at build time. With an SBOM prototype with pearls, yes. Definitely.
So just to repeat it,
That's good enough to have a pearl.
Yeah, you said there's PEP
725.
725. Okay, so that's I will definitely look into that. Hello. And then the other thing was called, sorry.
Estron.
Estron.
ESSTRA.
Estra. Okay, cool. So I'll look at those things. Thank you very much.
You can go to github.com/Sony,
Uh-huh.
the Sony company.
Yeah.
/Estra.
Amazing. Thank you. Any?
Raise your hand, Name-san. Or you can go to this guy there.
Amazing. I will. Hello. We have one question over there. If I still have time for one question, yes.
It occurs to me, it's not so much a question, it occurs to me that if you simply syscall tracer run, you will discover every dynamic object that's loaded.
I built a tool exactly for that with strace. It's painful because every single field has to be adjusted.
And does it not enough because you find exactly this, but then you don't know vector.
All right, that's enough.
Yep.
All right. Thank you very much. Good job. Thank you.